All right, thanks very much, Eduardo. Over to you.
Yeah, thanks a lot for the invitation. Hello, everyone. Um, I am Edoardo Debenedetti, a PhD student at ETH Zurich, and welcome to the presentation of our work, Privacy Side Channels in Machine Learning Systems. This is joint work with Giorgio Severi from Northeastern University, Nicolas Carlini, Christopher Shokatchu, Matthew Jagielski, Milan Nazar from Google DeepMind, Eric Wallace from UC Berkeley, and my advisor, Florian Termer, who's also at ETH. Yeah, so I guess yeah, you all know how good large machine learning models are at doing all sorts of things, from generating images, generating text, classifying, and all those cool things. However, they're not so good for privacy, and that's and we have many examples up to now from language models at the times of GPT-2, diffusion models like Stable Diffusion, but even production systems like GitHub Copilot, and as we've seen very recently, even ChatGPT memorize and even generate, reproduce exactly training data when they're asked for them, or sometimes even accidentally, like the latest example for ChatGPT. And that's a pretty big issue, both for copyright issues as it can be as it's a concern for Stable Diffusion or GitHub Copilot, but yeah, mostly for privacy because models can output personal PII, personal identifiable information that aren't meant to be extracted from these models, and and privacy in machine learning has been studied for a few years now, and we do have methods to assess privacy leakage of machine learning models, and we also have a basic understanding of why ML models memorize the training samples, and they mostly memorize samples that are either hard to classify because, for instance, are outliers, or often samples that are repeated in a training set. And how do we assess privacy leakage? We usually assess privacy leakage with what we call membership inference attacks, which, as the name suggests, are attacks, so they can be used by an adversary, but they're also often used to audit the privacy of machine learning models with under some sort of adversarial lens. And with a membership inference attack, what we try to do is to try to distinguish between two worlds. Given some target image. So for instance, here we have the image of this dog, and we want to distinguish, we want to understand whether we are in the world, whether this image of a dog was part of the training set of the model that we are auditing slash attacking, or in the world where this image is not part of the training set. And it's possible to do that because models are usually overconfident in the samples that were part of the training set. So, for instance, in the case where the sample was part of the training set, the model is going to say that, yeah, this is a dog, and I'm 75% confident that this is a dog, and 25% confident that this is a cat. However, if the sample was not part of the training set, the model is going to be less confident. So, for instance, it may say that it's still going to classify correctly the image, but this time it's going to be less confident, saying that it's a dog with a 56% confidence. And so, thanks to this, it becomes fairly easy to distinguish between these two worlds, especially for images that are outliers or that are repeated many times. However, there is one small issue with how, or at least the incompleteness with how we have studied privacy of ML models so far. And the incompleteness is that models are usually part of a broader system. And we have seen so far that when we study directly the model as if it were in a vacuum, we do have some leakage, but this leakage is still weak. However, what we do in this work is that we find some side channels that show that if we consider the model as part of a much broader system with training set filters, output filters, query filters, and other components, then the leakage becomes stronger. And yeah, and in our work, we study training set filters like deduplication. We study also some defenses against attacks, like poisoning defenses. We study query filters where we yeah, where that can be used to filter inputs to the model and output filters that prevent the model from generating given model outputs. And yeah, and so we find these side channels, and yeah, we describe them to give a better understanding of how we should analyze privacy of these ML systems. And let's start from training set filters. One specific training set filter we focus on is deduplication. Deduplication is a practice of, as the name says, deduplicating training data. And this is usually done for both privacy reasons, because previous work uh, about extracting training data show that the duplicated data are more likely to be extracted, but also for privacy, for performance reasons. The DALI 2 blog post mentions that the models trained on deduplicated data have usually better performance. And so, yeah, this is the main reason why deduplication is applied, both for a privacy reason and a performance reason. And the duplication is fairly simple. We collect all the data that we want to train our model on, and then we look at whether we have data that are equal or very similar to each other's. And if they exist, we delete them, either all of them or all but one. And then once we delete them, then we train the model. We can have, as I mentioned earlier, exact deduplication, where we with which we deduplicate data that are exactly the same, and near deduplication or approximate deduplication, where we deduplicate data that are not exactly the same, like these two images here. They're different cuts of the same image. But they're not, if you match pixel by pixel, they're not the same, but they are similar according to some metric, which, for instance, for images is could be the cosine similarity of some embeddings of a given model. And we can also, as I mentioned earlier, either delete all the duplicates or keep one of the duplicates, depending on the use case. And and we show that we can exploit deduplication to amplify the privacy leakage. And the way how this works is actually fairly simple. Assuming that we can poison the data set that is being collected, let's say if the data set is crowdsourced, and we want to see whether another user added their sample to the training set, then what we can do is to add if that specific sample, for instance, we want to target this image of a puppy, we want to see whether this puppy was part of the training set before deduplication is applied. We add the image of the same puppy with a different label, for instance, with the label of a cat, assuming that we are training dogs versus cats classifier. And what's going to happen is that if the image was part of the training set, then our images are going to be deleted, both mine and the one that was already there. And then the model is going to be trained on neither image. So nor the one with the label of the dog, nor the one with the label of a cat. And so at inference time, once the model is going to be trained, when we pass the image to the model is going to just see a regular dog and classify the image as a dog. However, if the sample was not part of the training set before deduplication, only our poison sample is part of the training set, then our sample is going to go through deduplication, is not going to be deleted, it's going to be used for training, and there at inference time, the model is going to classify the image as a cat. Not always, but it's very likely, but at least it's going to have a very high confidence, at least higher than normal, for this image into the cat class. And this is basically how our deduplication side channel works. And so as you can see, it's really easy to distinguish. It becomes quite easy to distinguish between the two worlds, where the original image was part of the training set before deduplication, and the world where the image was not part of the training set before deduplication, making membership inference easier. As I mentioned earlier, we can either have exact duplicates or approximate duplicates. In the case of exact duplicates, we just add one sample that is exactly the same. In the case of approximate duplicates, we add samples that are similar to the target sample, but are far enough apart one from the other. In this way, if the sample was not part of the training set, all our images are going to be far apart from each other, and they're going to be they're all going to be kept and they're going to go through deduplication without being deleted. While if the sample was there, then all these images are going to be considered duplicate, and then either all of them are going to be deleted or just one of them is going to be kept. And we can show that indeed the privacy leakage is really big, giving near perfect membership inference when we do exact deduplication, when we delete all the samples with member like AUC close to one, which means again near perfect membership inference. And we show also results on in the other settings where we delete all or like all but one the samples. And you can see that again in the case where we delete all the samples, which is not so common, we get near perfect membership inference. But even in the case where we do approximate duplication and keep one of the samples, which is the what we would consider to be the most common setting for real world deployments. The success rate of the attack is still very high with very high true positive rate at quite low false positive rate. And I guess most of the people here are actually not interested in images, but in text. And so I guess you're wondering, well, okay, images are one thing, text another thing. How would this work on text? Let's say that we don't have any experiments of this, but we believe that this attack is also possible on text. Let's say that the target string that we want to see whether it's part of the training set is A, B, C, D, E. Then we can create approximate duplicates in the form X, B, C, D, E, A, X, C, D, E, and so on and so forth, so that the duplicates again are one token slash character slash portion of text away from the target sample, but two from the other, and this way we follow the same scheme as we follow for images. If we were to do membership inference without these additional samples and without the duplication, we could just look at what's the likelihood of the model to output this string. If the likelihood is high, then it's we consider we can conclude that the string was probably part of the training set. But in this case, since deduplication is applied, we have many more data points, many more samples that we can use for our attack. And thus increasing the confidence of the attack and increasing the privacy leakage. And now I guess you will wonder, okay, should we still use deduplication? Because you've seen that we show that deduplication increases the privacy leakage quite a lot. And so it's a very legitimate question to say, well, then should we use it or not? While duplication could potentially make privacy worse, the risk posed by not using it and having models just spitting out training data because they're duplicated is much higher than having someone poisoning the data set. And so we believe that still for cases where we care about empirical privacy, so no, we don't really care about provable privacy, then we should probably still use the duplication. And we will see later that even for provable privacy, actually, it's more complicated than it seems. Moving on, we've seen that indeed we can exploit training filters to amplify privacy leakage, but this is just one of many components. Another among the other components that we study, there's also output filters, as I mentioned earlier. And one output filter that is being deployed to real-world applications are memorization filters. And memorization filters are basically filters that prevent outputs that were part of the training set to be shown to the user. So for instance, in this case, we ask ChatGPT to repeat the first few sentences of Harry Potter, which is a copyrighted book. We expect this to, since it's high quality text, to be maybe a part of the training set of ChatGPT. And indeed, ChatGPT refuses to reproduce the text after very few tokens. And however, if we ask the model to give us the same text but with some changes, some swaps in characters, we see that the model still does output the text, showing that in this case the filter didn't kick in. And so I guess it's fairly clear to you now that we can use this type of attack as a membership inference. We can see when the filter kicks in and when the filter doesn't kick in. And this is indeed what we do in our paper. In some cases where we can actually disable the filter completely, like for GitHub Copilot, we can have perfect membership inference because we can ask Copilot to repeat a given chunk of code. If Copilot refuses to repeat the text when the filter is active, but it repeats the text when the filter is not active, then we just get a perfect membership inference. But even when we cannot disable the filter, we can still get a pretty strong attack by simply asking a model to repeat a given string, our target string multiple times. For instance, we can ask ABCD, 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 and then to continue with ABC. And expect the model to complete with D. If the model does not output D, then probably some filter kicked in and ABCD was part of the training set, as we have seen earlier for Harry Potter. And yeah, and basically we can use this attack for even for extracting training data. We come up with a simulated scenario where we use GPT Neo so basically we attack GPT Neo, we create a Bloom filter on the training data, adding to the training data of GPT Neo 1000 OpenSSH key, and our aim with the attack is to fully extract these 1000 keys. And how we can do this is again we can follow the canvas that I described earlier, where we can ask the model to repeat a given string, and we ask. Assume, of course, I forgot to mention that we can do this when you know that a string has a fixed prefix. For instance, in the case of OpenSSH keys, we know that a string is always the key is always going to start with this key with this string here. And then we ask the model to complete token by enumerating all tokens. And whenever we observe that a model refuses to output a given token, then it's very likely that the token was part of the private key that we're trying to reconstruct, and then we select this and we move on with our attack. And by doing this, we can extract around 90% of the private keys with around 300,000 queries per model, which is a big number, but it's still fairly reasonable. And another interesting thing that we can do is to reverse engineer dataset properties. For instance, in the case of Copilot, we can reverse engineer what's the date cutoff of the training data. So what's the date of the latest code that was part of the training set. And we know from Copilot's official documentation that Copilot is indeed implementing a filter, I guess, to prevent copyright issues for people who use Copilot for the company they work for. And however, we don't know exactly how it works. It's probably doing some sort of fuzzy matching. And so what we do is we ask Copilot to continue or repeat chunks of code that were in several commits of TQDM, which is a popular Python package that's open source on GitHub. And we observed that before a given date, sometimes the Copilot repeats the code, sometimes it doesn't, suggesting that the filter is kicking in. But then after a certain date, in particular October 2021, Copilot is always repeating the code without any issues, thus suggesting that the filter is not kicking in anymore. And while it was sometimes kicking in before, so we cannot really use it for reliable membership inference, the fact that it's always kicking in after a given date suggests that indeed everything that comes after the date is not part of the training set and thus is not be filtered out. Yeah, so we have seen that all these different components can amplify privacy leakage, and thus the question is quite natural. How can we prevent this? One simple answer could be, well, why do we not use differential privacy? Differential privacy is a tool that it's been around in privacy research for quite some time now, and there are ways to train ML models so that they are differential private. What does differentially private mean? It basically differential privacy bounds the influence of trained data points on the final model, and by doing so, by bounding this influence, it prevents the model from memorizing the samples, for being overconfident, and yeah, for there are several ways to train ML models with differential privacy. One of the most common is, very roughly speaking, doing stochastic gradient descent, but while adding some noise at every iteration of SGD. What differential privacy needs to for the guarantees analysis is the sensitivity of the algorithm that we wanna make differentially private. And the sensitivity is a measure of how the output of the algorithm changes given a change in the input. And while if we know what's the sensitivity of an algorithm, then we can provide formal guarantees on the training. However, the formal guarantees hold for the model itself, not for the overall system. If our model is part of a broader system and is not just a model deployed in a vacuum. And indeed, we show that, for instance, deduplication has very high sensitivity because by removing or adding one sample, we can have influence on many, many more samples. And so we show that indeed, if we do differential privacy in a naive way, meaning if we just train a model with the PSGD while applying deduplication, which is something that has been recommended by previous literature, it's not a good idea because the assumptions that are made for the privacy theoretical bounds for the privacy guarantees of the PSGD do not hold anymore, and so when we run an attack, we show that the attack is much more successful than it should be if the theoretical bounds we're holding. And so we show that it's really important that to consider the overall system also when we employ components that are in principle private. And the overall takeaway of our paper and of this talk is that when we think about privacy, both empirical and let's say theoretically guaranteed, we should really be careful and consider the whole system, how the different components interact together, and what adversaries could do when they interact with the system itself. Thank you very much. I'm happy to take any questions you may have.
Super cool. Thank you very much. Yeah, I guess I have a yeah, I really like this actually. I think especially there was a nice demonstration about using it to estimate the date cutoff for the training data, right? I think once one is in, then there's a lot of really interesting attacks that can be done. I'm wondering, like, what are deduplicators doing wrong?
Sorry?
So what are like deduplication tools? What are they doing wrong in this case?
Uh, I think that there's nothing wrong in what they do because the problem with deduplication is more like, I guess, a fundamental issue of deduplication itself, and is that with one sample we can influence many other samples. So for instance, in the case where we are adding the our approximate duplicates, only adding one sample is going to influence uh, four, or for instance, in our paper, we actually end up using 8 approximate duplicates. It's going to influence the behavior of 8 more samples, which is going to have a large impact on the final model, and especially if these samples are outliers, like in our case, because we mislabeled them. So in principle, there's nothing wrong with deduplication itself. It's not that we are doing deduplication in the wrong way. It's just that probably if you want to do deduplication to be somewhat privacy preserving, we have to rethink that and how that works. To be honest, I I have no clue of how more private deduplication could could exist. But yeah, in principle, there's nothing wrong with how we do deduplication.
Yeah, I think it's to me at least a relatively new frontier of privacy to consider deduplication. And I mean, excuse me, the deduplication certainly is doing nothing wrong in terms of deduplicating, right? This seems to function perfectly rationally and sensibly.
Yeah.
Yeah, it just doesn't
And
consider
and
privacy, right?
And the same goes for output filters. Again, output filters have uh, have actually unbounded sensitivity, and then one can think about that with like an extreme example where let's say we have a model, we create a Bloom filter based on on the training set of that model. And what we can then do is to swap the model with a model trained on a completely different training set, completely disjoint. The model is going to have epsilon zero in terms of it's going to be perfectly private on the original training set. But then if we consider the overall system, since the Bloom filter or like whatever filter we're using is based on the previous training set, then it has still the very bad privacy that it had on the original training set. And so it's very tricky because yeah, you have all these components that interact together, and you need to understand how to make them interact together in a way that still preserves the properties that each of them has. I think I'm not a cryptographer, but I know that there are some examples of cryptography primitives that are secure if you take them by themselves, but then if you combine them together in a naive way, the overall cryptographic protocol you get may not be secure anymore. It's kind of the same here, where you get, for instance, deduplication and differential privacy. If you combine them together, they may not work as well as you would expect.
Yeah, and they did not hear, yeah, either, right? That's really interesting. And thank you very much for the text examples as well. That's always very nice. Like when you see the images come up, we're always like, oh yeah, image attacks, but how about the LLMs? And I think this, yeah, membership inference on copyrighted training data, this was really nice, especially with the
Yeah.
in-context learning example. Like, yeah, did you try just this one example or?
No, not yet, but it's my plan for the next month to play a bit with text and try something like this. Uh, the problem is that training models from scratch is quite for for image models we had to train couple hundred models for doing membership inference, and training text models from scratch could be a bit too expensive, and so ideally we'll try this on fine-tuned models, but usually fine-tuned models tend to not memorize as much the fine-tuning data as if they were using from training from scratch. But yeah, let's see.
Yeah, it feels more like one is giving a task to the organizations who train those huge models, right? By
Yeah,
I mean, I remember I was chatting with a guy from Andreessen a few months ago, and he described it to me like security is always a man on fire business. Until there's someone on fire, nobody reacts. But once you find that you can mine all of the copyrighted data directly from the LLM, this feels like a fire kind of situation.
yeah.
That's super nice. Okay. I guess not so many questions. And I imagine 18 December, people are flying back from Europe and getting ready to rest for the coming few weeks. So um, I'll stop the recording.